In this video, we're going to go over some examples associated with mathematical induction. So let's say if we have this statement, 3 plus 7 plus 11 plus 4n minus 1. Let's say that's equal to n times 2n plus 1. Now let's test it out with some numbers. Let's see if it's true for the first term. So the first term in this sequence is 3. And n is 1, which represents the sum of terms on the left. So we only have one term, so the sum has to be 3. So if we replace n with 1, this is going to be 1 times 2 times 1 plus 1. 2 times 1 is 2, and 2 plus 1 is 3. 1 times 3 is also 3. So it's true for n equals 1. Now what about n equals 2? Will it be true for that as well? So on the left, we have the sum of the first two terms. That's 3 plus 7. On the right, we're going to plug in 2 into that expression. So it's going to be 2 times 2 plus 1. Now 3 plus 7 is 10. 2 times 2 is 4 plus 1, that's 5. And 2 times 5 is 10. So it's true for n equals 2. Now, is it true for n equals 3? So this time we need to add the first three terms. That's going to be 3 plus 7 plus 11. And on the right side, let's replace n with 3. So it's going to be 3 times 2 times 3 plus 1. Now 3 plus 7 is 10. 2 times 3 is 6 plus 1, that's 7. 10 plus 11 is 21. 3 times 7 is 21. So it's true for n equals 3. Now this indicates that this expression might be true for all terms, but it's not a guarantee. It could be true for the first 3 terms, but for the 15th term it might be false. So we need to come up with a way to make sure that it's true for any term. So let's say if it's not true for the 28th term. Instead of testing it 28 times, we need to come up with a general way to see if there's going to be some value that is not true. So what we're going to do is use a letter k. So we're going to assume that it's true when n is equal to k. So let's replace n with k. So it's going to be 3 plus 7 plus 11 plus 4k minus 1. And so we're going to assume that this is true. Our task is to prove that the next term is going to be true. And that is when n is equal to k plus 1. So on the left, we're still going to have 3 plus 7 plus 11 plus 4k minus 1. But then we're going to add the next term. And so the next term, we just got to replace k with k plus 1. So it's going to be 4 times k plus 1 minus 1. That's going to be the next term. Now on the right, this entire sum should equal this expression if we replace k with k plus 1. So everywhere you see a k, replace it with k plus 1. So it's going to be 2 times k plus 1, and then plus 1. I'm running out of space there. Now we need to prove that the left side and the right side are equivalent to each other. Now notice that this expression is equal to k times 2k plus 1. So therefore, this portion of the equation has to equal to k times 2k plus 1. So we can replace it with k 2k plus 1. So how can we prove that these two sides of the equation are equivalent to each other? Feel free to pause the video and try it. For this example, the best thing to do is to combine like terms, distribute, and FOIL. So let's focus on this expression. Let's distribute k to 2k plus 1. So it's going to be 2k squared plus k. Now let's distribute the 4. So we're going to have 4k plus 4 minus 1. On the right side, we're going to have k plus 1, and let's distribute the 2. So it's going to be 2k plus 2 plus 1. Now we can add 4 and negative 1. 4 minus 1 is 3. And here we can add 2 plus 1. 2 plus 1 is 3. On the left, let's combine like terms. So we have 2k squared, k plus 4k, that's 5k. And on the right, we need to FOIL. So we're going to have k times 2k, that's 2k squared, and then k times 3, which is 3k. And next, 1 times 2k. And finally, 1 times 3, which is 3. On the right side, let's combine like terms. 3k plus 2k. So on the left, we're going to have 2k squared plus 5k plus 3. And on the right, we're going to have the same thing. 3k plus 2k is 5k. So the left side is equivalent to the right side. So that's how we can prove that the original statement is true for any term, or for any value of n. And so that's the basic idea behind a mathematical induction. Now let's try another example. So let's say that 1 to the third plus 2 to the third, and then up to n cubed, let's say it's equal to n squared times n plus 1 squared divided by 4. So let's show that it's true for n equals 1. So 1 to the third, that's going to equal 1 squared times 1 plus 1 squared over 4. Let's see if that's true. 1 to the third is 1. 1 squared is 1. 1 plus 1 is 2. And 2 squared is 4. 4 divided by 4 is 1. So it's true for n equals 1. Now let's try another one. N equals 2. So we need the sum of the first two terms. So 1 to the third plus 2 to the third power. That has to equal 2 squared times 2 plus 1 squared over 4. 1 to the third is 1. 2 to the third is 8. 2 squared is 4. 2 plus 1 is 3. And 4 divided by 4 is 1, so we can cancel that. 1 plus 8 is 9. 3 squared is 9. So it's true for the second term. If you want to, you can test out the third term. But this is enough for now. So we're going to assume that n equals k, and it's true when n is equal to k. So we're going to have this expression, 1 to the third plus 2 to the third plus k to the third. And that's going to equal k squared times k plus 1 squared over 4. Now, assuming that n equals k is true, or that the equation is true when n is k, we need to prove that it's also true if n is k plus 1, the next term. So we're going to have 1 to the third plus 2 to the third, and then k to the third. The next term after k is k plus 1. Now on the right side, everywhere you see a k, replace it with k plus 1. So this is going to be k plus 1 squared, and then replacing this with k plus 1, that's going to be k plus 1 squared divided by 4. Now we need to prove that the left side of the equation is the same as the right side of the equation. Now what do you think we need to do next at this point? Now recall that this side is equal to that side. So therefore, we need to replace everything up to k to the third with this expression. So we're going to have k squared times k plus 1 squared over 4 plus k plus 1 to the third power, and that's going to equal what we have on the right side. So how can we show that this expression is equal to that expression? Well, the first thing I prefer to do is combine these two into a single fraction. So I'm going to multiply k plus 1 to the third power by 4 over 4. So now I can write these two as a single fraction. So it's going to be k squared times k plus 1 squared plus 4 times k plus 1 raised to the third power divided by 4. And that's going to equal k plus 1 squared times, I can add 1 and 1, which is 2. So that's going to be k plus 2 squared divided by 4. Now let's get rid of the fractions. So I'm going to multiply both sides by 4. So these will cancel. Next, I'm going to take out the GCF, k plus 1 squared. If I factor out k plus 1 squared, on this side I'm going to get a k squared. Here, there's 3 k plus 1s. I took out 2, so there's 1 left over, and there's a 4 in front of it. So it's going to be plus 4 times k plus 1. We don't have to make any changes to the right side, so I'm going to keep it the same. Now, these two are already equal to each other, so I got to show that this expression is equal to k plus 2 squared. So let's begin by distributing the 4. So 4 times k, that's 4k, and then 4 times 1 is 4. Now, we have a trinomial that can be factored. So we need to find two numbers that multiply to 4 and add to 4 at the same time. So that's going to be 2. 2 times 2 is 4, 2 plus 2 is 4. So we could factor as k plus 2 times k plus 2. And so we can rewrite the left side as k plus 2 squared. And that's equal to the right side. So we've shown that the left side and the right side are equal for the next term, k plus 1. So therefore, it's going to be equal for all terms. And that's how you can use mathematical induction to prove that a certain expression is true for any term. Here's another one. Let's say if we have 1 plus 2 plus 2 squared, and then 2 to the n minus 1 is equal to 2 raised to the n minus 1. Let's test it out with a few numbers. So let's see if it's true when n is 1. So the first term is 1, and on the right side, let's replace n with 1. So that's going to be 2 to the first power minus 1. So that's 2 minus 1, which is 1. So it's true when n is 1. It's true for the first term. Let's see if it's true for the second term. So we need to add the first two terms. So that's going to be 1 plus 2, and then let's replace n with 2. So 1 plus 2 is 3. 2 squared is 4, and 4 minus 1 is 3. So it's true for the second term, or when n is 2. Let's see if it's true when n is 3. So on the left, let's add the first 3 terms. So it's going to be 1 plus 2 plus 2 squared. And that has to equal 2 to the third minus 1. 1 plus 2 is 3. 2 squared is 4. 2 to the third, that's 2 times 2 times 2, which is 8. 3 plus 4 is 7. 8 minus 1 is 7. So it's true when n is equal to 3. So we're going to assume that it's true when n is equal to k. So we're going to have this expression 1 plus 2 plus 2 squared plus 2 to the k minus 1 is equal to 2 raised to the k minus 1. Now, let's prove that it's true when n is k plus 1. So the next term, replace k with k plus 1. So it's going to be 2 k plus 1 minus 1. And then replace this k with k plus 1. So we need to prove that the left side and the right side are the same. The first thing we need to do is replace this expression with 2 raised to the k minus 1 because they're equal to each other. So we're going to have 2 raised to the k minus 1 plus k plus 1 minus 1. The 1's cancel. 1 minus 1 is 0, so that becomes 2 raised to the k power. Now, how can we show that the left side and the right side are the same? Well, imagine if we set x equal to 2 raised to the k. This would be x minus 1 plus x. And we know that x plus x is 2x. So we would have 2x minus 1. And then if we plug it back in, if we replace x with 2 raised to the k, it would be 2 times 2 raised to the k minus 1. So that's what we now have at this point. Now let's focus on properties of exponents. So let's say if we have x squared times x cubed. When you multiply by a common base, you can add the exponents. X squared times x cubed is x to the 5th. So 2 to the 1 power times 2 to the k is 2 raised to the 1 plus k. Now 1 plus k and k plus 1 are the same. If you add 3 and 5, or 5 and 3, both ways you still get 8. And so that's how we can show that the left side is equivalent to the right side of the equation.